Okay, great. Um, so this is an effort that several people were involved with over many years, starting with Steve Andrews at the time Fred Hutchinson Cancer Institute, and he's now at University of Washington. He had a very nice particle Brownian dynamics code that we were really excited to integrate with VirtualCell and collaborate with them on it. And then we even put some novel features in the combination of VCell and SmolDyn. So here's Steve right here. He's a great guy. There's an excerpt from his website. So SmolDyn, I just want to make clear, SmolDyn is a standalone application. It's still actively developed. He even has a Python interface to it, if you'd like to script against it. We did an integration of SmolDyn about 10 years ago, and we did continue to do a little bit of development with that joint effort. But the features, the SmolDyn features that we integrated were those that existed at the time. We haven't upgraded since then. So it's SmolDyn 2.38 is what we're using, and right now he's at 2.72, and he has additional features like molecular crowding, rule-based modeling, and I'm sure there's several others that I'm not mentioning. So anyway, huge thanks to Steve. Without this, it would not be possible. So just super brief review of the way SmolDyn handles the transport and the chemistry. So we're talking about particles that are spatially resolved. They're essentially like spheres. Like they don't have a shape, but they have a size and a location, and they can have a state. They know what kind of molecule they are. And when we're looking at chemistry, say a bimolecular reaction, A plus B goes to some complex AB. Normally, we describe it with some macroscopically observable reaction rate, like K observed, and do sort of solution kinetics. So it would be the proportional concentration of A and the concentration of B and some kinetic constant. The way this is handled in SmolDyn, now I'm going to describe the most basic case, but there's a lot more degrees of freedom come in when you start dealing with membranes and reflective boundary conditions and all kinds of things. But this is the very basic is there's for each step, this is a fixed time step method. You have molecules that do random walks according to Brownian dynamics and their diffusion coefficients. And with some probability, if two molecules are going to react, what is done is there's an effective sort of radius of interaction that is a function of, could be a function of their actual size, but it's more along the lines of making sure that if two molecules discover each other or within a certain radius, then they can be made to react. So if they're not very reactive, you can make that sort of artificial radius arbitrarily small. This is derived from Smolakowski dynamics. I was thinking of going through this because there's sort of a very nice mapping of how you derive these sort of microscopic rates by solving a reaction diffusion problem or a reaction problem, which is really quite nice and resonates well with VirtualCell. But I'll defer to other descriptions of Smolakowski dynamics and go to smoldyn.org for more detail on SmolDyn. So when is spatial important? Say the localization of cellular processes that are not captured by the average concentration, right? Where there's behavior that is influenced by local concentration. That's something that That's one of the motivations for using spatial modeling. Stochastic, when's the stochastic compartment? When you have a few molecules, rare events, and or quantized or discrete behavior, or individual events can have large effects. And spatial stochastic, in some cases, you get sort of the both of those things simultaneously. You have a few molecules that can have strong effects, like say ion channels, and they can be spatially coupled, so that I have an example, kind of a toy example coming up that investigates this. And one of the things that we added to SmolDyn when we incorporated virtual cell is to create a hybrid method. Some of the molecules are treated as fields, and using reaction diffusion equation and partial differential equations, and the particles are handled within SmolDyn as particle Brownian dynamics. And just super briefly, the way this is kind of coordinated, both of them are fixed time step methods. SmolDyn takes a step, and its probabilities can be influenced by fields provided by virtual cell. It does a step. We take a histogram of that step. We send it back over to virtual cell. Virtual cell uses that as sort of a crude field in order to evolve its PDEs, and it goes back and forth. That's the sort of 30,000-foot view of that. And just sort of a pictorial view, like, you have the term, just to ground everybody, there's a deterministic PDE. And this is the same model. And of course, in virtual cell, you can have really very different mathematical representations with the same physiological and even geometric description. So in this case, the same geometry, but when we're solving fully PDE. In another case, we're solving the same system with particles and Brownian dynamics. So this is a paper that Boris did a lot of very nice theoretical work, and in collaboration with Igor Novak. And when you develop a numerical method, it's not enough to say, well, it looks pretty good. You kind of have to really rigorously show and prove that the solution method has very nice properties. So Boris, you can check out this this paper that goes into some detail. A couple of highlights. There's a sort of a sarcomere activation in a cardiomyocyte in figure 1 here, where you have sort of cooperative opening of ryanodine receptors, and they're stochastic, but there's local coupling. And in figure 8 down here, it's coalescence of clusters on membranes, and there's some cooperativity there as well. And I think this is, hopefully it'll play. Oh, great. This is a movie from that model. And of course, these were developed in virtual cell, so virtual cell models are available for this as a published VCell model on a database. So you can also look at that. So just going a little bit more detail, I'm not going to do this complete justice. I have kind of a toy cardiomyocyte coming up that's a little bit bastardized, but it illustrates some of the concepts. But in general, like individual ryanodine receptors, these are calcium channels that live in the sarcoplasmic reticulum of cardiomyocytes, and they can open spontaneously, but they usually don't. Usually there's something like, T tubules will have some kind of electrical excitation, L-type calcium channels, push, create some locally elevated calcium near the channel, and then the ryanodine receptors really reinforce that and blow it up, and it give a very robust contraction, right? This is excitation, contraction, and coupling. But the elevated, and then the idea is once the calcium's elevated, the probability of nearby writing receptors will opening will greatly increase, and then there's positive feedback. A few channels are open at a time. This is just what they call a calcium spark. You can see with fluorescence microscopy. If enough calcium is released in enough places, and there sort of elevates the overall calcium in a region, it can really set off a wave of calcium that can go across the whole myocyte. Now, this is a little bit artificial because I think this only happens when you take like an isolated cardiac cell and myocyte and put it on a glass slide under the microscope. It's not being normally there's this whole thing is paced within the heart, but these are observed behaviors and really quite neat. Okay, so just as a little bit of restating what I said before. There's one limitation in virtual cell is when doing stochastic in general, and this is something we're working toward resolving. We were a little bit prescriptive on what kinds of kinetic laws we would provide, what we would allow when mapping to stochastic events. Mass action kinetics map very, very nicely. But there are cases when other non-mass action kinetics would also be helpful, and we're going to do that. But that's a current limitation of virtual cell. If there's a sort of a non-standard kinetic law, it may not allow you to put that process as stochastic. So here's I'll shoot over. Let me see how much time. I'm good. I have a little time. So this model I made fairly quickly. It's very loosely inspired by this. I guess maybe I should say SR and SR membrane. It's not really cytosol or membrane. It's the SR membrane. And I guess instead of extracellular, it's not really extracellular. It's the myocyte lumen. But in any case, I tried to put some of the dynamics in here, and what you end up getting is you have calcium. Okay, I'm sorry. The EC represents essentially the calcium stores. The SR lumen. The membrane's the SR membrane, and site is site. So here, there's a lot of calcium in the EC. If you open up a channel like the writing receptor, a lot of it can come out. Then you have channel dynamics. You have open and closed. The closed to open probability is influenced greatly by the calcium concentration on in the cytosolic side. And then in this model, it closes, just due at a particular time constant. Just the first order process. So and I took a snapshot in case the world collapsed and I wasn't able to demonstrate something, but I think I can. So let me try that. So, okay. So this is the kinetics that I'm talking about. They're not very realistic. There's a first order dependence of cytosol calcium on the channel opening. I think, if you look at some of the models for writing receptors, they're a little more interesting than that. But there's a cooperative behavior, and it definitely does depend kind of strongly, and I think non-linearly, on the local concentration. and that will come up into play shortly. So let me start by this one. So what do we have here? In this case, we're going to be treating see this force continuous button here on the upper right. This specifies that cytosolic calcium should be treated as a field. Now, extracellular calcium, or I'm sorry, actually SR-lumen calcium, is also treated as a field, but it's clamped, so it's really just a constant. It's like a number. You know, its value is 1,000. And in this particular model, the geometry is very, very simple. Geometry definition, you know, it looks like this. And some of the conversions work out very nicely. This is actually a 1 square micron patch. So later there'll be a kind of one-to-one relationship between molecules per square micron and molecules in the patch. You know, the density, since the area is unity. So in this case, let's start with three channels open and 22 closed, so a total of 25 channels. And I just wanted to make sure that there was something to see. If I spent more time, I could have created very long simulations with sort of small spontaneous openings that then died out, and then eventually there'd be enough critical mass that something big would happen. But I gamed the system a little bit by starting 3 at once, all open at time 0.
Jim?
Yeah.
I don't know if it's just me, but you've got very tiny text. I wonder if you could increase the size of your text or decrease the resolution on your screen or something.
I could decrease the resolution on my screen.
You need to do that with settings, I think.
Yeah, I'm doing it. In another window, I'm doing it. So let me see. Is this?
It's about your MacBook. That's not the settings.
I know, it's in another window. You can't see it. Is that better?
Yes.
Yep.
Thank you.
You're welcome. Okay, yeah, that's better. So let me close that for now. So let's start out by drag it up. Here we start with 3 open channels. I ran this earlier, but it doesn't take super long to run. It takes maybe a minute or 2. And let's just start at time 0. So there's 2 different views. There's like a slice view, or for surfaces, you can make a surface view as very kind of crude surface render, but it does the trick. So if you're looking at membrane things like the open channels and the closed channels, so at time 0, these are the closed channels. They're all the green ones only have 1 molecule, and by coincidence, right here, there's 2 molecules in the same bin. Now, so this is a histogram we're looking at. These are SmolDyn simulations, so they have continuous position within the surfaces and within the volumes. But when displayed in this visualization with virtual cell, it's going to appear to be sort of blocks that are colored by the counts. So if you just go a little bit farther, so let's say open already from, I guess we could rerun it in a very short term and see what interesting things happen there. From 0 to just 2.5 milliseconds later, you see that adjacent writing receptors, so here's the original pattern, and some nearby ones were excited enough to also open. So let's kind of explore that a little bit. Mm. Just a little bit, let's see, okay. So here I'm going in one of the planes in the XZ plane. I'm sorry, YZ plane that goes in X. So let's go back to, okay, this is essentially the first plane on the cytosolic side of the membrane. And after even 2.5 milliseconds, we get some very high local concentration of calcium. Now, don't shame me by using the wrong numbers. They're very high. I probably made them too high, but they're much higher than the surrounding area. And if you look in the post-processing results, and even if we sort of zoom in, well, or just look here. So the average cytosol calcium is still around 1, right? Even during that short time. And it goes up to, something fairly large. But if you notice in the area proximal to the membrane, it's around 1800. So it's much larger. And far away, it's very, very small. Again, of course, it shouldn't, resting calcium concentration shouldn't be 0. But again, don't look too hard at that. But I'm just expressing the point that proximal to sort of a rare event of a channel opening, the local concentration, especially of some of these electrolytes, it's designed to work that way, right? They can have very strong and very high local concentrations. So even after 2.5 milliseconds, you get that. And again, I've showed saturation. I'm going to make it a little bit bigger. But if we assume that 500 is a big number, which I think it is, then if we saturate, it's okay. What we're really trying to look at is how is the solution evolving, and if we notice that right now you have enough where one of the other, and if I change the scale, you can see that there actually is, if I change it to 100. And you can definitely see that there's calcium coming toward from this part, the gradients going down there. In fact, if we just look at auto range for actually just do this. You do have some calcium that has migrated over and has opened that channel. You can keep doing this. Just put back the sort of you notice as you move on, you're going to start getting other channels opening, which will then open up their neighbors, and you end up having some more dominant effects. If you look at it in the same way, like another thing that's kind of interesting is you can look at this is now, oh, this is zero. So here we're looking at a different view. These are where the channels are, and we can look and see where some of the different channels, the open channels, and the sort of the localization of the elevated calcium in that area. Now, this doesn't have to be calcium, but there could be some signaling involved in things like this. But of course, the entire purpose of these kinds of channels is to be able to have very strong all or nothing behavior, so that the cell contracts or it doesn't. So if there were signaling, it would likely be less dramatic, but there still could be some local response to say receptors and well, ligand receptor interactions and things like that. Okay, let's see. I think I'm getting close to the end of this presentation. Would anyone have any questions, or is there something that you'd like me to show you? Did it make any sense?
That was great, Jim. I just wanted to make one comment.
Sure.
You know, you showed that paper with you and Boris
Yeah.
on the hybrid. So I'm not sure you made it completely clear, but I think VCell is the only readily available tool that does hybrid deterministic stochastic spatial modeling. You know, there may be some others, but
At
I'm
the
not
time,
aware.
I think there weren't very many. I don't know if there's, I can't say for sure if there aren't
Yeah.
any.
So SmolDyn, you know, even the new versions of the standalone SmolDyn don't do this because this really took advantage of the fact that we had all this experience with our own PDE solver technology. And so it was, I wouldn't say it was easy, but it was natural for us to combine
Yeah.
the SmolDyn technology with the deterministic PDE solver so that you could have the best of both worlds. Because clearly it would be ridiculous to simulate calcium stochastically in any sort of large system like this,
Hmm.
because there are just too many calcium ions. But on the other hand, the ion channels that open stochastically are very important to model stochastically. So, yeah.
All right. Yeah, and there were, I guess, a couple of technical challenges during our integration. Like SmolDyn usually didn't have, thousands or tens of thousands of facets to represent its membrane. It would usually use fairly simple shapes. And
Yeah, I think SmolDyn does not use image-based geometries at all, right?
yeah, I don't. They may now, but at the time they didn't. And so there was some neat tricks to accelerate the computations and reduce the number of collision tests to surfaces and things like that. So we were able to get it reasonably performant, even using our general virtual cell geometries. So that was kind of a nice accomplishment as well.
Once again, just from the point of view of our students, it's very important to take advantage of the fact that you can do other kinds of simulations too. You can do ODEs, you can do just PDEs based on the same model. And, you know, it's always better to use ODEs first and see what the system behavior is. I see that you have an ODE simulation in there. So that, you know, you just get a feeling for what's going on. And then you can use that same model for the PDE system, for the stochastic system, and see if there are any significant differences in the overall behavior. But the stochastic simulations are more computationally intensive even than the PDE simulations. So you don't want to use them unless you really need to, unless there's a very small number of molecules in your
I mean, this
interest.
is actually side by side. This is one of the probably a decent comparison. The PDE solution is also spatial. There's gradients, but you're assuming that the channels are equal, uniformly distributed along the surface. And here, if you go look at different views, you're going to see different hotspots. And here,
You actually wouldn't have to assume that the channels are equally distributed along the
oh
surface.
yeah, I mean, but it's,
Yeah, I mean,
I mean,
you,
these channels, and you can actually have them diffuse around too while they.
Right,
while they're
right.
firing.
but you can localize the channels
Yeah.
in specific regions.
That's
Or small little, you know, tiny regions in the PDE as well.
But it's a little bit harder to do. It's sort of more natural when using particles. So I think that's not a bad uh not a bad situation in which the sort of hybrid particle PDEs work very nice. So okay, any other questions, or I can shoot over to just super quick discussion of moving boundaries. Okay, great.